Hello, everyone. Come on in. Feel free to ask me any questions. We got about 3 minutes before class starts, and some of you have already started chatting your first and last name. That's great. Go ahead and do that.
I did have a quick question.
Yes. What's up,
So,
Daniel?
I know we talked about last week with the grades not loading into Pearson. It
hmm
still hasn't updated, and I've done 7, 8, and 9 now. Is it still being resolved?
Have you contacted Pearson?
No, I've not.
Okay, let me just check real quick. I've got this thing going on in like a bunch of different classes, so I'm trying to remember exactly which one, what way yours is in particular behaving. So let me just check something real quick. And you said 7, 8, and 9?
Yeah, chapter conceptual and homework.
Okay,
Same for me.
gotcha.
And, and then with the homework, like the due dates keep on like switching up on me.
Yeah,
So
I like today I pushed 9 and 10 back specifically because actually I meant to do it last week and I thought I had done it, but it wasn't there, so I went ahead and
You
changed it.
did last week. They were set to the 5th, but when I checked last night, just in case, 9 was set back to the 2nd, so I had to
Yeah,
spend all evening doing it because I thought I had more time.
you did. I don't know what's going on. I don't know how that happened. So that's yeah, I apologize for that. I don't know how that's happening. Yeah, so this class, this is what I was checking. This class, it seems to be going through, just not for everybody. So I've got a lot of chapter 9, chapter 8, chapter 6 homeworks, and they've gone through, but not everybody's. So yeah, I would say probably it'd be best to go ahead and contact your the mastering people. Actually, no. Okay, I just found out chapter 7 and 8 conceptual didn't go through at least. Oh, and here's the other ones. That column just appeared all of a sudden. So yeah, it looks like 7, 8, and are not loading for anyone, but 9 is loading for everybody. 6 was loading for everybody. So that's the state we're in. Let me double check something and make sure. Yeah, all of those are set to sync. What's probably going to have to happen is I'm probably going to have to erase those in my grade book and then redo them, sync again, and that hopefully will take care of it. In fact, let me do that right now while I've got you guys here. 7 and 8 seems to be the ones that aren't working. 9 is working okay, so I'm going to homework assignments for 7 and 8. Maybe that's part of the problem. Maybe I got the wrong ones loaded up. Yeah, that's it. That's probably what's going on. So I'm going to say delete. Still got more people coming in. Okay. Okay, so I just erased all that and now I'm going to try to resync chapter 7 and 8. So Uh, tonight, hopefully, chapter 7 and 8 will be corrected. If it's not, then definitely go ahead and contact Pearson. But I think this might take care of it. I just discovered what I think could have been causing the problem. There was a extra grade category that I don't use, and evidently somehow chapter 7 and 8 were in that published, but not chapter 7 and 8 that was actually in the appropriate grade category. So that could have been what happened. And hopefully, this latest syncing that I had just finished, yeah, it literally just finished, hopefully, that'll take care of it. So let me pull up the grades again just to check, see if it worked. It might have already worked, in other words. Yep,
Uh, I, I,
7 and 8's in now.
okay. I had a two questions I was wondering about.
Hmm.
One is I know I did my second face to face. The first one said it was out of 100, but the second one's currently saying it's out of 25.
Yeah, there's two different versions on there. The one that students took with me, I had actually counted it out of 100. The one online, I just chose not to change the point, so it's listed as 25. So when it
Will they
says out
be
of
worth
25, you
this?
divide your score by 25, but when it says out of 100, that's an actual percent.
Yeah, I was just wondering like if they were worth the same amount or not. That
Yeah,
was it.
it's only one category, only one column where I put in the test. That's the only one that's counting, and that one's in the 100 point system, so that all of them count the same.
Okay. And the other one is was the final also face to face or is that online?
Yeah, the final is a face-to-face one, and that, like I said, you have like a week and a half at the end of the semester to get that done. But yeah, that one's definitely a face-to-face.
Okay. Thank you.
Okay. So it looks like we got a couple people that missed the online test. I will open that back up. There will be a penalty, but that's sort of the whole point, everybody. Remember, I make the online test so that you have a little bit of more confidence and you have a good score going in, so that makes you feel better about your test. So you should expect a online test immediately before, and in fact, every two chapters period is online tests. But in addition to that, there's almost always going to be one just before the face-to-face test, and the whole purpose in that is to give you a little bit more confidence and to catch those few stragglers that didn't do their practice test. So definitely check that out. I will open it back up for the people that missed on that one, but we'll have to take off some points for being late. So keep an eye on that, and you need to be checking your Canvas to make sure that you don't miss any assignments. I put the due dates on there, and I know Canvas reports when they're due, and they even have a little report off on the right-hand side saying, "Hey, this is due next." So if you're just not going into Canvas frequently enough, then you're going to continue to miss those. So every time you do, that's just what you're supposed to have is a pretty much 100 average on your online test, and you guys are getting less than that because you're missing. I say you guys. I think one person's missed two. Everybody else has just about missed one. Actually, it might have been two people that missed two. But anyways, anybody else have any questions? So actually, weird thing about the test, I just looked it up again. Are those grades that I just finished fixing, and there's two categories that work great. And then there's two categories that didn't. So there's a 8 homework and a 7 conceptual that's now filling in perfectly. But there is a oh now it's got all of them. Now 7 homework, 7 conceptual, 8 homework, and 8 conceptual. I just had to do it twice. So now all of those are showing. Hopefully that's working for you guys. Also keep in mind that when the actual test occurs that a given practice test is for, uh, immediately, if you didn't take that practice test, you're going to get zeros for it because the whole purpose of the practice test is to prepare you for the test. I'm not going to give anybody any extra credit for taking a practice test after they've taken the test because that's sort of defeating the purpose. So keep that in mind. And let's go ahead and get started unless anybody has any questions that you're curious about or anything. Anybody have any questions?
Uh, it says I've taken all the quizzes and tests on there, right? Like, because I know I've taken them all. I just want to make sure there's not like a glitch claiming there's not.
Oh, gotcha. Let's double check. Usually that's not a problem because that's all within the same system. No, it looks like everything you've got. I don't see any, yeah, I don't see any missing spots in there on yours.
All right, thank you.
No problem. Yeah, I don't see a one. So good job, Colin. All right, so when we last talked, there was a little bit of a problem. I dropped a negative. I might have changed an A to a B. So what I thought I'd do is work something sort of equivalent to one of the problems in the end of the chapter, just to give you an idea of how we could go about solving for a head-on elastic collision. So remember the condition for momentum to be conserved is the summation of the forces is equal to zero. Then the condition for elastic collisions is that the total kinetic energy is conserved, or specifically, it's called an elastic collision if the total kinetic energy is conserved. Those elastic collisions are more likely to occur at the macroscopic scale when two rigid objects run into each other, like pool balls, specifically pool balls that wouldn't be rotating because they can actually cause a whole different set of problems. The fact that they rotate and roll and have all that friction. But if you imagine two ceramic hockey pucks or two really hard steel hockey pucks running into each other, that's a good example of a elastic collision. But you can tell immediately upon hearing them collide that it's not technically an elastic collision because the fact that you hear a noise at all means that sound waves have been created and it takes energy to make waves. So clearly, some of the energy from the system is disappearing. Hopefully, it's a small amount, so it doesn't matter. At the microscopic level, it's a lot different. Specifically, the only thing that could steal, because there's no quote unquote smaller particles that could cause friction and all this stuff. At the microscopic level, you expect more elastic collisions because really the only thing that would tend to steal any energy from the system is like a Coulomb force, which is the force of attraction between oppositely charged particles, or the force of repulsion between similarly charged particles. So a positive and a positive repels, a negative and a negative repels, but a positive and a negative attract. Because of that, you can actually get a little bit of energy added to the system or a little bit of energy removed from the system, and that can make them non-elastic. But other than that, and even that's not necessarily a huge factor in a lot of cases. So just remember that if they talk about it on the microscopic level, a lot of times it is going to be elastic. So keep an eye out for that word. Now, let me start off with what we know. I'm going to give you a problem specifically where we have a head-on collision. So I want to find out what are VA prime and VB prime for an elastic head-on collision in which the summation of the forces is equal to zero. So remember, that's the condition that's required for momentum to be conserved, is the summation of all the forces acting on the system has to
Yes,
be
sir.
equal to zero. Yes. And
I
yeah,
can't see your screen.
thank you for reminding me. Wrong one. Actually, so far I hadn't written anything anyways, but yeah, I do appreciate you telling me. Why is this not going up? There it is. There it is. Okay, now I got it. Thanks for that. Coming up. Okay, so the big trick that I showed you last time was taking the kinetic energy and treating that as a difference of squares. By getting the 1/2 MAVA squared minus 1/2 MAVA prime squared on one side, and the 1/2 MA, or excuse me, 1/2 MB VB prime squared minus 1/2 MB VB squared on the other side, you can immediately get rid of the 1/2s, and then you can factor out that VA prime minus V, or excuse me, VA prime squared minus VA squared into VA prime minus VA, parentheses VA prime plus VA. And then that can be divided by the conservation of momentum equation, and you get this really nice expression. So for starters, conservation of momentum gives us MAVA plus MB VB is equal to MAVA prime plus MB VB prime. That's just conservation of momentum. The expression that we got by combining kinetic energy equation, conservation of kinetic energy, with this conservation of momentum, gave us basically that VA minus VB is equal to the negative of VA prime minus VB. In other words, the difference in the velocities changes sign from before to after the collision. So, for instance, if you had like 3 and 5, or I should say 3 and 5 for VA and VB, 3 minus 5 would be -2. After the collision, you would have VA prime minus VB prime would be +2. So that's the big result. What we're going to do now is make use of these two equations, 1 and 2, and I'm going to write 2 a little differently. I'm going to say VA minus VB is equal to negative VA prime plus VB prime. And from that, I'm going to go ahead and solve for let's solve for VB prime. So VB prime is going to be equal to VA minus VB. That takes care of this one and this one. And I've already taken care of this one. Now I've got to pull the VA prime, which is a negative on the right hand side. I got to bring it to the left hand side, which means it's going to be a positive VA prime like this. So what I have now is VB prime in terms of VA, VB, and VA prime. We know VA and VB. That's the whole assumption is we know MA, we know MB, we know VA, we know VB. We're trying to find VB prime and VA prime. So I'm going to call this equation 2 prime, and I'm going to plug 2 prime into equation 1. So what I have is MAVA plus MBVB equals MAVA prime plus MB. Now this is where I'm going to plug in VB prime. Double check my algebra, make sure I got all the signs right on that VB prime. I'm pretty confident I did, but it would be excellent if one of y'all could confirm that. I'm going to go ahead and plug it in here. That should be VA minus VB plus VA prime. So I'm double checking VA minus VB. That looks right on the left hand side. Minus VA plus VB prime. That looks good on the right hand side. Then pulling the VA prime to the left. That's going to be VA minus VB plus VA prime. Okay, that all looks good. Now what we can do is start grouping terms in such a way that we can solve for VA. So I'm going to go ahead and distribute to get rid of these parentheses. So MAVA plus MBVB is equal to MA VA prime plus MBVA minus MBVB plus MB VA prime. So this right hand side, I can see, for instance, that this term and this term both have a VB prime. So I'm going to combine those two and take these and put them on the other side. So in doing that, I'm going to get MAVA plus, oops, I didn't mean to switch to red there. Hold on. Not that it matters too much, but MAVA plus MBVB is equal to, or actually, let's not do the equals yet. Let's go ahead and pull the MBVA over. That'll be minus MBVA. That takes care of that one. That takes care of that one and that one. And now I want to pull the negative MBVB over here, so that'll become a positive MBVB. That took care of that term. The right-hand side is now going to be MA. Notice they both have plus symbols in front of them, and they're both multiplied by VA prime. So I'm going to factor out the MA plus the MB and leave that multiplied by VA prime. Not only that, I'm going to combine like terms on the left and not in the, well, I'm going to combine terms that have the same velocity. So for instance, I have a term with a VA and another term with a VA, so I'm going to put those two together. So let's look, for instance, at this one and this one. That's going to give me MA minus MB, all that times VA. That takes care of that. Now, in the other case, I've actually got MB plus MB, so I'm going to write this as 2MB VB, and that's all equal to MA plus MB times VA prime. So now I'm in a spot in a position where I can go ahead and solve for VA prime, and this will be a actual final answer for half of the problem. VA prime will be equal to MA minus MB over MA plus MB. All that will be multiplied by VA. And then in addition to that, I'll have 2MB over MA plus MB. All that times VB. So that is, in fact, the general response for a head-on elastic collision between two particles. I didn't make any assumptions about the masses being the same. I didn't make any assumptions about one of them sitting still or anything like that. I just got that result. Now that I have that, I can plug this back into 2 prime to get VB prime. So plug this into 2 prime. So now I'm going to get VB prime is equal to VA minus VB plus MA minus MB over MA plus MB, all that times VA plus 2MB over MA plus MB. And that's a really terrible looking B that I made up here, so I'm going to try to fix that a little better. Okay, and this is all multiplied by VB. Now, I think it's pretty obvious that we need to get a common denominator. So what I'm going to do is I'm going to make this VA. I'm just going to pull that out in front. And for this term right here that I just put the check on, that's going to have MA plus MB. And all this is going to be over MA plus MB. But I have that where I just multiplied it by MA plus MB, and now that's the VA term, so I'm going to combine it with this VA term, which is, notice there's a plus in front of the parentheses, so I just distribute the plus. So it'll be plus MA minus MB, and then all of that's divided by MA plus MB, like this, and then all of that is multiplied by VA. So that takes care of the two ones that I have checks on. I'm going to do the same thing with this negative VB term. So in this case, I'll just put this like that. In this case, I'm going to factor out the VB, which I'm going to say is positive. And now the coefficient that I have for the negative one is going to be negative MA minus MB because I'm multiplying by MA plus MB over MA plus MB, which is just 1. But now I've got to also add to it the plus 2MB. All that, of course, will still be divided by MA plus MB. And then all of this, of course, is multiplied by, oh, I already had that VB. Oopsie. And actually, I did the same thing over here. This VA I'd already counted. I don't know why I multiplied again. So I think I just got excited about putting too many, about making sure I put enough check parentheses around it. So that should do it. Oop, got a student that accidentally been kicked out, evidently. So we've got that. And I actually don't need this square bracket either. So now what I have is all this. You can see that the 2MB minus MB is just going to give me MB, and I'll have MB minus MA. So in this case, the result is going to be VB prime is equal to, notice the MA plus MA is 2MA, and the MB minus MB is just going to be 0. So that's going to be 2MA over MA plus MB, all that times VA. And then for the other one, it's going to be MB minus MA over MA plus MB, all that times VB. And that's it. So this is the most general solution you can actually have for a head-on elastic collision. And that's it. Anybody have any questions on that? So I sort of did this to make up for the careless mistake I made on the previous derivation that might have shocked y'all into thinking it was very complicated or something like that, when it's really not supposed to be that complicated. This is fairly straightforward algebra. Your book actually mentions this. It's I want to say problem 34 in the textbook. Yeah, it's problem 34 at the end of chapter 9. And they give you the answers on page 239. And what I got was 2MA, yep, and MB minus MA, that's right. And then the other one was for VA prime. I got VA was MA minus MB and 2MB. Yep. So this actually did get the results. So I'll say C number 34 and page 239. So anybody have any questions on that? All right, so let's work another problem. In this case, we're going to do example 9-9. So let's say example 9-9. Now, again, this is really helpful for you to have your book available, but I'm going to read it to you either way. And example 9-9 says a nuclear collision, a proton of mass 1.01 unified atomic mass units traveling with a speed of 3.60 times 10 to the fourth meters per second has an elastic head-on collision with a helium nucleus. The mass of the helium nucleus is 4.00 unified atomic mass units. Initially at rest, what are the velocities of the proton and helium nucleus after the collision? As mentioned in chapter 1, here's a conversion factor for the unified atomic mass unit, but you won't need it. Assume the nuclear collision takes place in nearly empty space. So what we have is the mass A is the thing that's moving, and I'm going to refer to this as the actual proton, and its mass is 1.01 U. VA is equal to 3.60 times 10 to the fourth meters per second. And what I'm just going to say is this is for the proton. Just because I'm trying to stick with the A and B subscripts instead of putting a P for proton and a H for helium or a A for the alpha particle or whatever. The
I'm sorry,
mass,
what unit is a U?
it's called a unified atomic mass unit. Basically, it's very, very close. If you take Avogadro's number and do 1 divided by that and realize that that was in terms of grams instead of kilograms. So then you multiply it by 1/1000th and you'll actually get the conversion factor. It's mentioned in chapter 1, but we really don't cover it until you get to like chapter 17. So
Okay,
that's a 242 class question.
thank you.
No problem. This is going to be 4.00 U. And again, the conversion factor is 1.66 times 10 to the negative 27th kilograms is equal to 1 unified atomic mass unit. And what we do know is VB in this case is 0, so that's sitting still. And we want to know VA prime equals question mark and VB prime is equal to question mark. So in this case, the masses are not the same. So what we have to do is we're going to write out conservation of momentum, and conservation of momentum says MAVA plus MBVB is equal to MAVA prime plus MBVB prime. But in this case, we have that the initial velocity of the B particle, it's a target particle, so it'll be sitting still. So instead of this, we have MAVA is equal to MAVA prime plus MBVB prime. Now, we also have the other equation that we derived from using the fact that it was a elastic collision and momentum was conserved. That was normally the difference in the velocities VA minus VB is equal to the negative of VA prime minus VB prime. But in this case, we're using VB equal to 0. So in this case, I'm going to get VA is equal to VB prime minus VA prime. In other words, distributing that negative gave us that. Now, if I decide to go ahead and solve this for VB prime, then VB prime will be equal to plus VA prime. Now I can plug that back into the top expression, which I'm going to call 1, and I'm going to call this, actually, I'm not going to call that last one 2. I'm going to call this one 2. So plug 2 into 1, and what I get is MAVA is equal to MAVA prime plus MB. Now here's where I substitute my value of VB prime. It's going to be VA plus VA prime. Now I can distribute that, and that'll become MAVA equals MAVA prime plus MBVA plus MBVA prime. That suggests it would be really smart for me to get those VP prime, VA prime terms together. And I'm going to put the other terms on the other side, which gives me MA minus MB times VA. That's what comes from me pulling this over here with this one. And now on the other side, I'm going to get MA plus MB times VA prime. So that gives me VA prime is actually equal to MA minus MB over MA plus MB. And remember, I told you this seems a lot like the formula for the acceleration of the Atwood machine. It's the same formula. The difference is instead of VA, they would have a G there, and you would be solving for A instead of VA prime. So now we know what the VA prime is supposed to be, and that's the velocity of the proton after the collision. So I'm going to go ahead and plug in those numbers. We get 1.01 U minus 4.00 U divided by 1.01 U plus 4.00 U. Notice the U's completely cancel out. Notice also that we get a negative. That's because the bigger mass is the one that's sitting still as the target. So the small mass is going to hit it and bounce backwards. That's why we're getting a negative velocity here. And this velocity right here was 3.60 times 10 to the fourth meters per second. So if I take the 1.01 minus 4, and I divide that by 1.01 plus 4, that gives me this quantity right here is negative 0.5968. So if I multiply that times 3.6 times 10 to the fourth, that gives me VA prime is equal to 2.15 times 10 to the fourth meters per second negative. And that just means that the proton is actually going to hit the helium nucleus and fly backwards with a pretty significant velocity. Now that I have that, I can use equation 2 to figure out VB prime. So from equation 2, I know that VB prime is equal to VA plus VA prime. So I can say VB prime is going to be equal to 3.60 times 10 to the fourth meters per second plus VA prime, which is negative 2.15 times 10 to the fourth. And actually, let me see if that math works out right. 1.01 minus 4.00. Yeah, that should give me 3 sig figs, 3 sig figs. Oh, yeah, so the 5 is not a non-significant figure. So let me fix that. I probably should have carried an extra digit, which would have been 49 instead. So I could say 49 like that. And then in that case, the 9 would not be a significant figure. So that's what I'm going to do here as well. I'm going to call this a 4-9 and not let the 9 be a sig fig. And that's 4 meters, 10 to the fourth meters per second. So I'm going to say 3.60 minus 2.149 equals 1.451 times 10 to the fourth meters per second. So that means the velocity of the alpha particle or the helium nucleus is 1.451 times 10 to the fourth meters per second after the collision. Anybody have any questions on that? And just to look, they got 1.45 times 10 to the fourth and negative 2.15 times 10 to the fourth. So we are in agreement with the textbook's answers too. So everybody see the process that you go through with a head-on collision? You can actually use this formula. In fact, if you wanted to memorize it, it's just I'm not going to give you that on your equation sheet. I don't even give you this one on your equation sheet, but I would highly recommend that you learn how to derive this because this is just a really easy thing and I don't supply this equation. So bare minimum, I would say you'd want to memorize that, but I would say it's a lot easier to memorize it if you figure out how to derive it yourself. So just give that a try. That would be a really good skill for you guys to learn. I'm getting ready to show you another technique for 2 and 3 dimensions, and that's a much bigger deal. So that's one that you're going to have to memorize anyways, just like this one. So I would say it would be a good start for you to try to do this one and then do the 2-dimensional. Anybody have any questions on that? All right, your book chooses to talk about an inelastic collision section, and it says specifically if two objects stick together as a result of a collision, the collision is said to be completely inelastic. And the reason they use that wording is in physics, we don't necessarily hold ourselves to only the reality. For instance, when we're running an experiment with an accelerator, like what we use, like the Large Hadron Collider or something like that, we don't restrict ourselves to the reference frame that we live in, which is attached to planet Earth. Sometimes we jump to a different coordinate system. And that coordinate system, for instance, might be one that's moving with respect to the Earth. And there's a lot of good reasons to do it. For instance, if you took, let's take this problem that we just did. We had an alpha particle whose mass was about 4 times the proton's mass, and we had the proton moving in at 3.6 times 10 to the fourth meters per second. Now, because the proton is 4 times less massive than the helium nucleus, we might choose to jump to a reference frame in which the alpha particle is moving instead of sitting still. Now, this alpha particle is 4 times as massive, so what we'd like to do is go into a system where the total momentum is zero. Again, you don't necessarily need to know why, but the big thing is when we jump to that system where the total momentum is zero, in that frame, the uh, basically the proton is moving at one speed, and then the alpha particle is moving at another speed such that the total momentum is zero. So, because the proton has 4 times as much mass in that new frame, the velocity of the proton will be 4 times larger than the velocity of the alpha particle. And they're in opposite directions, so the two momentums add up to give you zero before the collision. After the collision, of course, momentum is conserved, so the momentum is still zero, so the two particles are stuck together, and not only that, they're not moving. So they've literally lost all their kinetic energy in that particular frame. That's why they call it completely inelastic, because you've lost all the kinetic energy. That being said, you don't necessarily need to know all that, but you do need to know that perfectly inelastic or completely inelastic is the word they're using, means that basically the two particles stick together. What they do for that is they solve a ballistic pendulum problem. So I'm going to go ahead and do the same thing. So what I want you to think about is let's imagine a ceiling. Oops. Let's imagine a ceiling, let's say right here. That's supposed to be the ceiling. Now, hanging from the ceiling is a big, massive block of wood, if you will. Wood or metal with some rubber inside or something like that. The main thing is it has a really huge mass. And that mass, I'm going to say, is big M. And additionally, we have an itty bitty mass that is a projectile, little mass, a mass little v, little m, but it's been shot out of a gun, so the velocity is really large. So we're going to use conservation of momentum to solve for the velocity of the cube bullet system just after the bullet becomes embedded in the actual cube. Now, when that block of wood does this, it's then going to take off and swing up to some new height, let's say, like this. And that new height is something that we can use to figure out what the initial muzzle velocity of the rifle was. So what we're wanting to figure out ultimately is what is H in terms of V. So I just put H as a question mark there because that's sort of what we're looking for. So first off, collision. The summation of the forces is equal to zero. Therefore, P initial is equal to P final. And this is one dimensional during this collision. Basically, the bullet's being shot horizontally. It rams itself into and burrows into the block of wood, and then that block of wood takes off horizontally as well. And the instant it starts to move, we ignore it. Okay, we're finished with that. We're just trying to figure out what that velocity is. So conservation of momentum says that little m times big V is going to be equal to little m plus big M times, now I'm going to say this thing, once the bullet is embedded, so it'll be a little hole like this, and it'll have the bullet inside of it like that. And now the block, I'm using it as if it's red because I want it to look a little different, and it's moving with a velocity little v. So in this case, that's the final velocity right there. And I can find out what that final velocity is. That final velocity, little v, is m over m plus m times big V. So now we have the velocity of the block with the bullet stuck in it. And what we're doing now is looking at a conservation of energy problem for figuring out how high the block will go now that the bullet's in it. So now we're going to go to a conservation of energy problem. And that, of course, is UI plus KI plus work in is equal to UF plus KF plus work out plus E loss. Now, this is not one of those ones where we're actually making much use of the extra terms that I provided, so I'm going to put zeros on all those. Not only that, initially we have zero potential energy and we only have kinetic energy, and then afterwards it's going to come to a stop, so we'll have zero kinetic energy and only potential energy. So basically what we have is the initial kinetic energy is going to be equal to the final potential energy. So that gives me 1/2, because kinetic energy is 1/2 mv squared. So it's going to be 1/2 the total mass, m plus big M, and times the velocity, which is that little v squared. That's going to equal m plus big M times g times h. So what we can see is from this standpoint, the m plus m is clearly going to disappear. And we can get, for instance, that h is going to be equal to v squared over 2g. Now I can put in what that v is. Remember, that's the lowercase v. So I can say 1 over 2g. And then in place of the v, I'm going to put in m over m plus big M. That's got to be squared because the velocity is squared. And then the big velocity has got to be squared as well. So now I can see that h is equal to m squared over 2g times m plus big M squared times the muzzle velocity squared. And in fact, it's really more about the muzzle velocity that I really want to know. So I'll solve for the muzzle velocity and say that the muzzle velocity squared is equal to 2 times g times h times m plus m quantity squared divided by lowercase m squared. Therefore, the muzzle velocity, this is the big V, equals V muzzle, is equal to the square root of 2GH times M plus big M squared, all that divided by little m squared, which gives us V equals V muzzle is equal to m plus m over m times the square root of 2gh. Anybody have any questions on that? All right, so that's a nice little application. This was pro example 910, by the way, so I should write that down. This was example 9-10. Anybody have any questions on that? Make sure I look at the chat in case you guys are saying stuff to me. I forgot to put that over here. It doesn't look.
Was V muzzle the big one or the small one? It's hard to tell with
Yeah, I
these in
know.
upper and lower cases.
Yeah, I'm trying to make them bigger. The V muzzle is supposed to be the big one because I was picturing the itty bitty bullet with the big velocity versus the big mass with the itty bitty velocity. So that's what it was supposed to be. So this V right here that I have in the box is the big V.
Okay.
Mhm. If it helps, you can go through and put these bars on it. That's what I occasionally do. Uh,
So where did the little one go? Because it was there to a point, but then
yeah,
it just kind of
this is the
disappears.
little one right here. You see that?
I
And
don't see a cursor or anything.
okay, I was
Oh,
drawing it in red dots. That's the
yeah.
V squared. That
Okay.
is what we determined V to be. So
Oh,
I
okay.
plugged this in here to make up for
All right.
that. Does that make sense?
Okay. Yes.
Yeah, it's easy to lose when you're doing lowercase and uppercase, and I didn't put anything special up there to indicate it. So
All right.
hopefully that's a little more
Okay.
clear.
Thank you.
No problem. And this would be that one, and that one, that one, and that one, that one. Okay. All right. Now that we have that, let's move along. There are actually some other types of problems you can solve in this. There's the railroad cars again. This is a decent one. I'm going to go ahead and do it, even though I had originally thought about not. So let's say example 9-11. It says, for the completely inelastic collision of the two railroad cars we considered in example 9.3, calculate how much of the initial kinetic energy is transformed to thermal or other forms of energy. So what we had there was MA equals MB is equal to 10,000 kilograms. And we had VA was equal to 8.0 meters per second, and we had VB was equal to 0, and we were supposed to figure out what VA, or excuse me, what V would be, which is the final velocity, after they stuck together. Conservation of momentum, so summation forces is equal to 0, therefore P initial is equal to P final, which gives us 10,000 kilograms times 8.0 meters per second is equal to, after they collide, they're actually going to stick together and they'll have a total mass of 20,000. So 20,000 kilograms times, in this case, this new velocity v. And you can see that this new velocity is in fact going to be 4.0 meters per second. That's what we found when we did example 9.3 that it referred to. Now what they're wanting us to do is figure out how much initial kinetic energy is transformed into thermal energy. And all that requires us to do is calculate the initial kinetic energy and then compare that to the final kinetic energy by subtraction. So kinetic energy initial would be 1/2. Remember, only one train car is moving initially, times 10,000 kilograms times 8.0 meters per second squared. So this is basically going to be 8 times 8 is 64. So it's going to be 3.2 times 10,000, basically, or 32 times 10,000. Uh, 0.5 times 10,000 times 8 squared gives me 3.2 times 10 to the fifth. And that's the kinetic energy in joules. The kinetic energy after which is one half of, oh, in this case it's 20,000 now because it's two cars stuck together. And now their velocity is 4.0 meters per second because we just worked that out. You can see that this is going to be basically 1.6 times 10 to the fifth joules. So you see that K final is actually equal to 1 half K initial. So basically the answer is 1.6 times 10 to the uh, 6 is the loss of kinetic energy. So K lost is equal to 1.6 times 10 to the fifth joules. And that would be, you know, basically energy that was converted to heat. If you, it might not be obvious if they just banged into each other once, but if you bumped the two parts of the train cars that were bumping together, if you bumped them together a bunch of times and then touched it, you would find that the metal where they touched would actually be quite hot. So that tells you, of course, when one touches it one time, it's going to be, a fraction of that as hot, but it's still getting hotter. And of course, it's a massive piece of material. So you'll learn later that that's a significant amount of kinetic energy or a significant amount of energy to heat that piece of metal up. Additionally, it's going to make a loud sound. That sound, it requires a pressure wave, i.e. a sound wave. That takes energy, so on and so forth. If it was parts of a car running into each other as opposed to these rigid parts of a train car that are meant to collide and then clamp to one another, what you'd get is some deformation of the metals when two cars collide, and that metal being compressed and dented and stuff like that steals away a lot of energy. To some extent, some of that energy is going to be stolen, even though they're not going to permanently deform very much by the two train cars running into each other. Anybody have any questions on that? All right, what I want to get to now is the big technique that we're going to use to solve collisions in 2 and 3 dimensions. So we're going to start off with a simple example, but I need to first off give you guys an idea of what 2 and 3 dimensions looks like when we're doing an actual collision. So what we're looking at here is a mass MA moving with a velocity VA, and without a loss of generality, we're perfectly justified in assuming that this initial particle is moving in the positive x direction. And without loss of generality, we can go on the assumption that the other particle is sitting perfectly still. So this particle has a mass mb, and VB is 0. Now, after the collision, what we're going to have is, let's say, I want to draw this again, like that. And what I have is a velocity VA, or excuse me, VB prime. Forgot I drew the red one there. And that angle is theta B prime. In addition to that, I'll have the other particle leaving at an angle theta A prime. And in this case, it's a mass MA and its velocity is VA prime. So that's what happens after the collision. So conservation of momentum can be written as follows. the summation forces is equal to 0. Therefore, P initial is equal to P final. That's a vector equation, which becomes more obvious now that we're doing it in 2 dimensions instead of 1 dimension. So first off, I'm going to say Pi sub x is equal to Pf sub x because I'm wanting to work out the x components. In this case, what we have is basically just Ma VA because it's moving parallel to the x-axis. It's moving in the positive x direction. We don't have any other components. That's the only thing that's moving. MB is not moving, so I don't have a term there. But this has got to be equal to the sum of the two x components. So the x component of MB will be, well, let's start with MA first. So the x component of the MA momentum is going to be MA times VA prime times cosine theta A prime. And the x component of MB will be MB VB prime cosine theta B prime. So I'm going to call that equation 1. Now I've got another issue. The initial momentum in the y direction is equal to the final momentum in the y direction. But again, remember we said without loss of generality, we can assume that particle MA is moving parallel to the positive x-axis, and therefore it has no y component. So in this case, I get 0 is equal to MA VA prime. Now the y component is given by the sine of theta A prime. And similarly, MB VB prime times the sine of theta B prime is equation 2. So now we have equation 1 and equation 2, and that is just conservation of momentum. You see you have two equations, therefore you could have up to two unknowns. And let me show you an example with this real quick. So we're going to go to example 912. Example 912 says billiard ball A moving with speed VA equals 3.0 meters per second in the positive x direction, figure 919, strikes an equal mass ball B initially at rest. The two balls are observed to move off at 45-degree angles to the x-axis. Ball A above the x-axis and ball B below the x-axis. That is, theta A prime is 45 degrees and theta B prime is negative 45 degrees. What are the speeds of the two balls after the collision? So that's what we're trying to work here. So we're going to start off with saying MA equals MB is just plain M. We're going to say VA is equal to 3.0 meters per second. VB is going to be 0 because they're sitting still. However, we want to know VA prime equals question mark, and we want to know VB prime equals question mark. What we do know is theta A prime is equal to positive 45 degrees, and theta B prime is equal to negative 45 degrees. Now that we have all that, we can apply the equations we just had. So equation 1, for instance, remember the masses are the same. So in equation 1, I can just get rid of all those masses. In other words, this mass, this mass, this mass are all not going to be there. So I'm going to get instead VA is equal to VA prime cosine 45 degrees plus VB prime cosine negative 45 degrees, like that. And now we can also say equation 2, 0 is equal to VA prime cosine, or excuse me, sine 45 degrees plus VB prime sine of negative 45 degrees. Now remember, cosine is what we call an even function, which means the left-hand side, left of the y-axis, is a mirror image of the right of the y-axis. So that even symmetry there means that the cosine of 45 is the same thing as the cosine of negative 45. Sine, on the other hand, is what we call an odd function, so its mirror image is actually upside down. So the sine of negative 45 is the negative of the sine of 45. So those are our big results. I'm going to go ahead and take equation 2. So from 2, we're going to say that VA prime is equal to, basically imagine I'm pulling the VA prime to the left-hand side, or let's say I'm pulling the VB prime to the left-hand side, so it's now going to be negative, and I'm going to go ahead and divide by sine 45, so I get the sine of negative 45 degrees divided by the sine of positive 45 degrees. And that, in fact, gives me that VA, because the two negatives, VA is equal to VB prime. So VA prime is equal to VB prime is our first result. Okay, so I'll circle that. Now I can plug this, which I'm going to call equation 3. I can plug 3 into 1. So now I can plug in the VA, which is 3.0 meters per second, is equal to VA prime cosine 45 degrees plus VA prime. Notice I've just substituted by replacing the VB prime with a VA prime. I've actually substituted 3 in times the cosine of negative 45 degrees. Cosine of negative 45 degrees is the same thing as cosine 45 degrees. Again, that's because of the evenness of that function. Now what we can do is we can see that 3.0 meters per second is equal to 2 VA prime cosine 45 degrees. Therefore, VA prime, which is also equal to VB prime, is equal to 3.0 meters per second divided by 2 times the cosine of 45 degrees. So if I do that, I take 3 divided by parenthesis 2 times cosine 45, close parenthesis, and that gives me 2.12 meters per second. So what I've discovered is VA prime is equal to VB prime is equal to 2.12 meters per second, and that's how we solve that problem. Anybody have any questions on that? All right. Now the next one is example 913, and this is where I'm going to show you the mathematical trick that you guys need to memorize. I didn't really do anything with solving this one for problem 912, but this one's going to require a little bit more, even though we do have the nice advantage that MA is still equal to MB in example 913. So example 913. It says a proton traveling at a speed of 8.2 times 10 to the fifth meters per second collides elastically with a stationary proton in a hydrogen target as seen in figure 918. One of the protons is observed to be scattered at a 60-degree angle. At what angle will the second proton be observed? So I'm going to say theta A prime or theta B prime is equal to positive 60 degrees. We're not sure which one, but it doesn't matter because protons are sort of identical, so we're not going to be able to tell which one's which anyways. At what angle will the second proton be observed, and what will be the velocity of the two protons after the collision? So we want to know what is VA prime, and we want to know what is VB prime. Okay, so we do have MA equals mb equals the mass of the proton. So now we can say equation one, since the masses are all equal, we don't need any mass at all. So I'm going to divide through them by them. But what we get is VA is equal to VA prime cosine theta A prime, which for just for the heck of it, I'm going to go on the assumption that theta A prime is the 60. And what we'll see is some symmetry that will allow us to reverse it, work it back again with theta B prime being the 60, and we get the exact same result, but with, the opposite conclusion about which one's which. So cosine theta A prime, I'm going to call cosine theta or cosine of 60 degrees plus VB prime. Well, that couldn't have went any uglier. So VB prime, okay, I stand corrected, times cosine theta B prime, like that. That's one of our equations. Now, our other equation is 0 is equal to VA prime sine 60 degrees plus VB prime sine theta B prime. That's equation two. Now I'm going to go ahead and, since this is an elastic collision, I'm going to go ahead and write out the kinetic energies, but I'm going to leave off the 1/2 because the 1/2 obviously cancels out. In this case, I'm going to leave off the masses because remember, MA equals MB, and I can just divide the whole thing through by that. So what I'm going to get is VA squared is equal to VA prime squared plus VB prime squared, like that. That's going to be equation 3, and this is from it being elastic. Does everybody see how that VA squared is equal to VA prime squared plus VB prime squared? All right, the big deal with that is, and you might notice right now, do y'all know of any type of triangle that you could make where VA is the hypotenuse, VA prime is a leg, and B prime is a leg, and the magnitudes would be related this way? What would that say about the triangle that has its magnitudes given by that equation 3?
Uh, sorry.
It's a
One
weirdly worded
second.
question.
Um, I was just looking over that since it's going to be the kinetics are equal to each other. Does that mean VA prime and VB prime is combined is? Yeah.
Do you recognize that this equation 3 sort of looks like a Pythagorean theorem?
I was just trying to think of since A equals no, wait, I realized what my brain was doing.
Oh,
Never
gotcha.
mind.
Okay, yeah. Sometimes it's a little confusing because you use the A's and the primes and the B's and all that stuff. There's just too many things going on at once. The neat thing is the initial velocity squared could be thought of as the hypotenuse of a right triangle, and then the VA prime and the VB prime would be the legs of the right triangle. So that would suggest the angle between VA and VB should in fact be 60 in one case and then 30 in the other, because the two should add up to give you 90. So that right there tells us that the answer should probably be negative 30. and that's something to remember. So when you have a head-on collision between two particles that have exactly the same mass, then the two particles are going to leave, making a 90-degree angle with each other's final velocity. But now we're going to go ahead and show you how to get that. What I'm going to do is take equation 1 and get all the VAs on one side. So 1 is going to give me VA minus VA prime cosine 60 degrees is equal to VB prime cosine theta B prime. Now what I'm going to do is square both sides. This is the part that you guys sort of need to remember. I'm going to square both sides, and that's going to give me VA squared minus 2VA VA prime cosine 60 degrees plus VA prime squared cosine squared 60 degrees. All that's equal to VB prime squared cosine squared theta B prime. Let's call this 1 prime. Now I'm going to take 2 and I'm going to put the two terms on opposite sides and square them. So 2 is going to give me basically VA sine 60 degrees is equal to negative VB prime sine theta B prime. And now I'm going to square both sides. This again is the part that you're supposed to be sort of memorizing. Notice this one's a lot easier when we square it. We just get VA squared sine squared 60 degrees equals VB. Oh, that's VA prime squared, by the way. Ooh, let me make sure I correct that. Uh, and this one's going to be VB prime squared sine squared theta B prime. And we're going to call this equation 2 prime. So now we can actually think about adding equation 1 prime and 2 prime. And the reason being is notice we'll get a VA prime squared times parentheses cosine squared 60 plus sine squared 60. That's going to be a wonderful thing that allows us to eliminate a lot of junk. So in adding these two, what we're going to get is VA squared minus 2VA VA prime cosine 60 degrees plus VA prime squared cosine squared 60 degrees is equal to VB prime squared times cosine squared theta B prime. Now I'm adding to that VA prime squared sine squared 60 degrees is equal to VB prime squared cosine squared theta B prime, like that. When we add these two terms, I just get VA. Actually, let me clean that up a little bit. When I add those two terms alone, I get VA prime squared, and this one I get VB prime squared because sine squared plus cosine squared is 1. So that's why that is so. Now that we have that, we know, or we have VA prime all by itself, we have VB prime all by itself, and we have VA, which we know, and VA prime, which we want to know, and we've got the theta equals 60 degrees. So now I have VA squared minus 2VA VA prime cosine 60 degrees plus VA squared. So that gives us the opportunity to actually figure out exactly what the VA and the VB is. The way we do that is we take equation 3 and we solve that for VB prime. So from equation 3, VB prime is got to be equal to, or VB prime squared has got to be equal to VA squared minus VA prime squared, like that. So if we substitute this equation into, let's call this new equation, let's call this equation 4, and let's call this one equation 3 prime, plug 3 prime into 4, and what we can get then is VB squared, we're going to say VA squared minus 2 VA prime cosine 60 degrees plus VA prime squared is equal to VA squared minus VB, or VA squared, excuse me. So this one's VA prime squared. Now you can see what happens. This VA squared cancels out with this VA squared, and we've got a couple different VAs in play here. I can pull this VA over here, and what we're going to get is 2 VA VA prime cosine 60 degrees is equal to 2 VA prime squared. You can clearly get rid of one of those VAs like that, and now you see that VA prime is just going to be equal to, I can also get rid of this 2,
Wait,
by the way.
wouldn't that be negative 2 VA prime?
It was negative on both sides. So when I pulled this one over here, that became negative with that negative, and this negative was already there. So that's why it's both of them ended up being positive. Does that make sense to you? Or can you see it now?
Yes.
Okay. So now what we have is VA prime is in fact equal to 2 VA cosine 60 degrees, and that's pretty much it. Now that we have that, we can plug in that 60 degrees. We could have actually just left it as theta A prime and then tried plugging in the 60 for that one, and then later tried plugging in the it for the other angle. But either way, we've ran out of time, so I have to finish this up next time. But we've got most of the way. I would highly recommend you guys trying to figure out the rest of this by looking at the example, and be prepared to finish it up next time. And we'll do center of mass as well. You guys are free to go. If you hadn't already chatted me your first and last name, please do. I know Ryan had a question. Ryan, you want to ask that question now?
Yeah. If we could go back to, I guess it was 910.
Okay,
I'm just having trouble here understanding how work's not expended in this situation. I guess it would, so we don't have
gotcha,
the displacement, I guess, is perpendicular in terms of like the force, which I guess
gotcha. So
centripetal
for
force.
starters, we're breaking it up into two pieces. There's an initial
Okay.
piece where you're doing conservation of momentum, and that's just the bullets in the air flying towards the block, and the block's just hanging there.
Okay.
And what we're imagining is conservation of momentum is going to dictate that immediately when that bullet starts to penetrate the actual block, eventually the block is going to bring the bullet to a stop, and the two of them are going to leave with the same momentum that the bullet had initially. That's why we said m, lowercase m, capital V, is equal to m plus m in parentheses times lowercase v.
Okay.
That allows us to solve for big V, which is or excuse me, that allows us to solve for little v, which is the velocity that the block with the bullet in it will have the instant it starts to leave. So all of that was done way before we did anything with conservation of energy. I totally get that you'd think maybe some work was put in by that, but even then, it's still not really accurate to think that way because both the block and the bullet are part of the system. So that would be an internal force, anyways, and energy exchange between the two is going to be handled by conservation of energy without any additional work to be added or stuff like that.
Okay.
So we wouldn't add that in. Uh, Once we have that, though, we now know the velocity of the m plus m moving, and then it's just a matter of I've got potential, or excuse me, kinetic energy of a block with a bullet in it. That's going to be converted completely into potential energy, and no air resistance is pretty negligible. So work done against that would be zero, friction would be zero, all that kind of stuff. That's why conservation of energy comes into play with just the Ki term and the U final term.
Okay. So I'm just so to use conservation of energy, you have to use that after the collision. Is that what you're saying?
Yeah, for this
Okay.
particular type of problem, it's like a twofold problem where you use momentum to work out what's going to happen from the collision. You can't use energy methods with that because that's a lot of stuff going on that energy would be problematic to calculate. But momentum just takes all that really easily. So you break it up into a conservation momentum problem that occurs, and then the block takes off with this new velocity, and then at that point it's a conservation of energy where kinetic energy is going to be converted to potential energy.
Okay. I'm just having trouble separating this from work because we spin stuff with steam, and steam is kind of like a bullet hitting something. So
All right,
okay, so I
yeah,
just need to okay. Thank you.
no problem. Anybody else have any questions?
Yeah, I had a question.
Yes, Melanie.
Um, so on the last problem that we did,
Mm-hmm.
yeah,
That one,
uh,
911 or
yeah,
912?
or nine, 913.
913. Okay. Oh, the very last one, the one we were working on.
Yeah,
Yep.
yeah. Um, well, you said, I just want to make sure real quick. You said that we could cross out the two, right, at the very end.
Uh, y- oh yes. So that two shouldn't have been
Okay.
there. Good job. Nice catch.
No, yeah, I just wanted to make sure 'cause I thought maybe the two came from somewhere
No,
else. And
that way when the notes go up, people will see that that was a boo-boo. But yeah, the two was gone.
okay, got it. And then on could you go to the because I didn't finish writing like the very first problem that we did. I just want to get
Okay.
a screenshot of that really quickly.
No problem. The very first one, the one that I did all this derivation stuff for.
Yeah, yeah,
Okay.
this one. I just yeah.
Ain't
Thank
it
you.
beautiful?
And yes. I was trying to make sure I get it all in my notes, but yeah. Uh and the actual question I had was a homework related question. It was a concept question if I could just ask it real quick.
Yeah, go for it. I'll
Yeah,
do my
so the
best.
the question, it was a true or false question, and it said, in any elastic head-on collision, the relative speed of the two objects after the collision has the same magnitude but opposite direction as before the collision, no matter what the masses are. And it said it was true, but like from what I understood is like sometimes the masses does affect it because if like a really heavy car hits a smaller one, then wouldn't the smaller one like
Right.
bounce back with like more like I don't know, higher velocity?
Yeah, I mean, it's good that you're thinking in terms of that because you're thinking physically what's going on. But
Yeah.
what you also got to remember is we're using physics principles that have stood the test of time.
Hmm.
And what we did was we took the conservation of kinetic energy, which is what's required for an elastic collision, which the question is asking about, and we
Yeah.
took the conservation of momentum, which is also required, and from that, we were able to basically factor the conservation of momentum, or excuse me, conservation of energy equation, such that when you divided that by the conservation of momentum equation, the masses completely canceled out. So that
Okay.
result that we got, the one that's right here, VA minus VB is equal to the negative of parentheses VA prime minus VB prime. That
Yeah.
is the reason that the answer is true because that's exactly stating it. The relative velocity changes sign before the collision compared to after the collision.
Okay. That makes sense. Cause I did cause while I was doing the homework, I was like, I do remember that we canceled out the mass, and that's why it didn't matter.
Yep.
Okay.
And that's just if you had conservation of kinetic energy with conservation of momentum. If it was an elastic collision, that wouldn't be the case.
Okay, got it. All right, that was my question. Thank you so
Good job.
much.
That was nice thinking. You have a good one.
Thank you. You too.
Bye bye. Anybody
Bye.
else have any questions? Actually, you're the last one. So I guess that's it. And I'm going to go ahead and say stop sharing and goodbye.